this. N2O4, which is a gas, would yield two NO2 molecules, and it is also a gas. So we have a very simple chemical reaction here. Now remember what we said in the very beginning, that an equilibrium expression is when we have the rate of the forward reaction being equal to the rate of the reverse reaction or the backward reaction. So we can first make an equation. So we are going to develop the equilibrium expression based on this concept. The rate of the forward reaction is equal to the rate of the reverse reaction. This is how we say it is an equilibrium expression. So now we are going to take a look at the forward reaction and the reverse reaction separately. So let's write down the forward reaction. Okay, so we have the forward reaction right here. And in the previous chapters, we learned about writing rate laws. So we're going to write a rate law for this reaction. And I'm going to put a subscript F here to stand for forward. And we do the same for the reaction constant. Now, in the rate law chapter, we learned that it's going to be the reactant being included in the rate law. And we usually look at tables to determine the coefficient, not the coefficient, the exponents. We want to determine the exponents by a table with a set of data. Because we are told, or we learn, that for the order of the chemical in the reaction, it has to be determined experimentally. But now something is changed a little bit, because this reaction is an elementary reaction. So what we can do is that we are going to use the coefficient in the as the exponent. Now you may say, well, is this kind of contradictory to what we learned in the past? Well, this is not true. The reason why we can use the coefficient in this particular scenario is because when we have the coefficient, it is expressing how readily it's going to react. If it has a coefficient of 1, then it means that they will have a linear relationship. As the concentration goes up, then the reaction rate would go up linearly. Okay, and this is what justified our action to put the coefficient as the exponent. And this is only true for elementary reaction. If it is not an elementary reaction, we cannot do that. So we're going to put a 1 right here, but it's going to be expressed implicitly. So this is our rate of the forward reaction. And now we're going to write the backward reaction right here. Okay, and we can do the same. And I'm going to use the R to represent the reverse reaction. And since we have a 2 for the coefficient, we're going to put a 2 here for the exponent. Let me draw a line right here. Okay, now with these two equations, we can now make use of this concept and put these two equations together and see what's going to happen. So we have Kf times the concentration of N2O4 is equal to the Kr times the concentration of NO2 squared. So we combine these two equations together to get this equation. And now let's rearrange the equation for a little bit. put all the reaction constant on one side. So this, we cancel out the Kr, and then we are going to put all the concentration on the other side. Okay, so these two cancel out. So what is remaining is an expression of Kf over Kr is equal to NO2 squared over N2O4. Now, expressing this is kind of complicated. So we are going to have a big constant, the capital K, with a subscript C here to stand for this fraction of the reaction constant. And this is how we get the equilibrium constant, and this is how we get the equilibrium expression as the product over the reactant, and this is how we get the coefficient to be the exponent.